Okay, so question one for momentum states that the resultant force acting on an object is slowly increased. That means force is increased. Which graph would show the variation of the momentum P of the object? So we have to think about force and momentum. How are they related? So basically, through Newton's law, we know that force is basically rate of change of momentum. So since they say force is increased, so we have to see that change of momentum is basically increasing, and we have a momentum time graph. So if we figure out momentum time graph, then the gradient of such a graph, that's P and T. So if we are working for momentum time graph, then we are looking for the gradient of this graph that would basically represent force. So in which of these diagrams we have to see whether gradient is increasing or not. So if gradient is increasing, that would mean force is increasing. If gradient is not increasing, that would mean force is not increasing, right? Because that's the question given. So let's see if we have any increase in gradient here. So no, that's decreasing gradient. Any increase in gradient here? So kind of appears yes. So this looks like fine. So this is an increasing gradient, right? So that would be the correct answer. C is a still decreasing gradient. D is all the way constant gradient. So I'll go with B. Okay. So if there is any question from your side, just speak up in the microphone or maybe give a message in the chat box. Otherwise, I'll understand and I'll expect that everyone understands the question clearly. Okay. So question one is done. Let's move to question two. It says an astronaut has a weight of 660 Newton when she is standing on the Earth's surface. सही ठीक है. Then the acceleration of free fall on the surface of Mars is this. What would be the weight of the astronaut? I think this one is pretty easy. It says astronaut has a weight of 660 Newton. So we can use mg to find out mass. It's 660 Newton. Mass is unknown. Let's take g to be 10 for simplification. This would give us 66 kilograms as the answer for mass of the astronaut. At Mars, the acceleration due to gravity is 3.71. So that's 71. That's 66 times 3.71. So what do we have? We have around 250 Newton. So that would be C. Then in question three, they say a stationary toy gun fires a bullet. Okay. So that's the bullet and the toy gun. So it fires this bullet. ठीक है. Which statement about the bullet and the gun immediately after firing is not correct. So we have to find out the incorrect statement here. ठीक है. So the force exerted on the bullet by the gun has the same magnitude as the force exerted. That's absolutely correct. There is nothing incorrect in this statement. The force exerted on the bullet by the gun is in the opposite direction. That's still fine. The gun and the bullet have the same magnitude of momentum. That is still fine because they are a system. So in an isolated system, momentum stays conserved. So it is conserved. That means D is the only option that shouldn't be correct. So basically, it says the kinetic energy of the gun must equal the kinetic energy of the bullet. No, that isn't correct because according to an elastic collision, what happens is kinetic energy of the system stays same. So for system, that means bullet and the gun, total kinetic energy should be same. It doesn't mean how, just imagine how fast the bullet is going to go and the gun is going to move that much faster. Answer is no. That wouldn't be correct, right? We are firing bullet, not gun. So D doesn't make sense at all, right? Then question four. It says a snooker ball has a mass 200 grams. Okay. It hits the cushion of a snooker table and rebounds. So let's say that's the ball. It hits and it rebounds. So what happens? The ball arrives at the cushion with 14. So that's initially 14 and it rebounds with -7 because it is changing direction. So it will be -7. The time in contact is 0.60 seconds. Okay, so average force. ठीक है. So we can simply use the equation where force is change in momentum over time So that would be final momentum minus initial momentum over time. So mass is given, that should be 0.2 times. Final velocity is basically -7, and initial velocity is 14, and time is 0.6. Once we simplify it, we are going to get the answer as uh, 7 newtons. So, which is option D. Negative sign shows that the question has assumed the other direction to be positive. What we have done this direction as the positive direction. Maybe the question has done this direction as the positive direction. So we are not bothered about the signs. Actual momentum change and force change would be 7 Newton. Question number 5. Which statement follows directly from Newton's first law? Okay, first law. So question number 5. A body remains at constant velocity unless acted upon by a resultant force. That seems pretty much close to the first law, because it says in the first law that a body at rest remains at rest, or a body in motion continues its motion unless there is a resultant force or an unbalanced force acting on it. So 5A is fine. So is this understood to all of you guys? Then question 6. Question 6 asks us, it says a box rests on the earth. Okay, well, we can see that Newton's third law describes how forces of the same type act in pairs. One of the forces of a pair is the weight, which W of the box. So weight W of the box is this. Okay, which arrow represents the other force? So basically, they refer us to us. They're referring to the question related to third law. So that has to be an action reaction pair. So if weight is the action which they have started up, so the reaction should be opposite to W. So that eliminates D and C, right? And the only option now left is A and B. So basically, I'm going to select A. Why A? Because weight is the force of Earth on anything. So if Earth is attracting anything like this, so the object should attract anything like this. However, B is more likely normal reaction. So B would not be correct. I'll go with A. So 6 should be A because that's the action reaction pair. Let's try question 7. Question 7 says, what describes the mass of an object? The force the object experiences due to gravity? Well, that's not mass, that's weight. The momentum of the object before collision, still that's not mass, that's force. The resistance of the object to changes its motion, yeah, that's correct, because that is inertia. So we can just realize it through an example. It is very difficult to stop a heavy object, and it is very easy to stop a light object, right? So why do they differ? Because it shows greater resistance. So it shows lesser resistance. So there is more inertia. So C refers to mass, which is correct. Now, question 8. Okay. Let's say the car has a mass m. A person needs to push the car in with the force F in order to give the car acceleration A. Okay. So let's say that's the car. So it requires a push F, and it produces an acceleration A. So according to Newton's law, this should be related as this. Okay. The person needs to push the car with a force of 2F in order to give the car acceleration 3A. Okay. In some other case, he needs to push the same car with a force of 2F so that it produces an acceleration 3A. Okay, which expression gives the constant resistive force? Okay, so there was some resistive force here. I missed that. So let's say that's F. So resultant force would be maximum minus minimum. So it should have been somewhat like this in the first case. So it should be F minus F is equals to MA. So this is still there. So for this equation, this should be 2F minus F is equals to M times 3A. So that would be 2F minus F is equals to 3M. Okay. So we have two equations, equation 1 and equation 2. They want us to find out the resistive force. I think we can simply just solve these up, and we are going to get this. F. So if I, kind of make F the subject here, I'm going to get MA plus F, and I'm going to plug this value here. So this becomes 2F. 2F is MA plus F minus F equals 3MA. So this would be 2MA plus 2F minus F is equals to 3MA. So basically 2F minus F is F, 2MA is here. If it goes to that inside, so on right hand side it becomes negative. So that means 3 minus 2 would be 1. So that would be Ma. So resistive force is Ma. So do we have an option here? Yeah, we do have an option here. That's A. That's nice. Good job. Then question 9. So for question 9, it says that each diagram illustrates a pair of equal pair of forces of equal magnitude. Okay, equal magnitude. Which diagram gives an example of a pair of forces that is described by Newton's third law? So for third law, we are looking for an action reaction pair. So action A, action is driving force, resistive force. Well, these are not action reaction pairs. Why? Resistive force is between tires and car. Driving force is basically of the engine and the car. So these are two different forces. B, Earth's gravitational attraction moon. Yeah, they both are same nature. That's perfectly fine. So I'll go with B. Let's see C. So C is incorrect. Why? Because they're saying it's weight and support force. See, support force comes from, the normal reaction, the contact between the surface. So that is what is supporting this object. And weight comes from Earth. So Earth and the support force, sorry, weight and the support force, they are not action reaction pairs. So C is incorrect. Let's try D. It says lift and weight. So basically, lift comes through air, or basically now you guys have done that air pressure, that was rho gh, and that is exerted by these engines. So it's basically an engine force. Weight is not the engine force, so they aren't the action reaction pairs. Still B is the correct answer. Okay, question number 10. It says a resultant force of 10 Newton X on a body for time 2 seconds. Okay, which graph could show the variation of momentum in time? So momentum in time. So basically, uh, we have a momentum time graph, right? And we are looking for a line whose gradient comes out to be 10 Newton. Why? Because the gradient of momentum time graph is the force. So we are looking for something whose gradient is 10. So let's see. A, if I select A, so I see basically it is like, if that's A here, so the change in momentum would be 10 divided by change in x-axis, that's 2. So this is not 10, that's 5. So A is incorrect. Let's try B. So change in momentum for B, that's, well, 20 divided by x, that's 2. So which is 10? So I'll go with B. If you see C, so it's 10 over 2, which is 5, which is not 10. And if you see D, it's 5 over 2, which is 2.5, which is still not 10. So I'll go with B. Okay. Next part of the question, question 11 says the acceleration of free fall on the surface of planet P is 1/10 of that on the surface of planet Q. On surface P, body has a mass of 1 kilogram and weight of 1 Newton. That means P has a mass of 1 kilograms and weight of 1 Newton. So let's find out the G. So G would obviously be 1 on planet P. And the other statement states that this is 1/10. This is basically 1/10 of Q. So Q should have an acceleration of 10 meters per second squared, right? That's the only reason. Then this statement would be true, right? So that's what happens at Q. So this is given. Then they say what are the mass and the weight? So mass actually is 1 and weight actually is 10. So I'll go with B. Okay. Let's try. Yeah, so I need a kind of break for, a couple of minutes. I'll be back. Okay, I'm not just ending this class. You can go through the questions. I'll continue from this. I need a break because I'm done speaking too much. So question number 12 says that water is pumped through a hose pipe at a rate of 90 kilograms per minute. So that's mass is 90, time is 1 minute, which is going to be 60 seconds. Water emerges horizontally from the hose pipe with a speed of 20 meters per second. What is the minimum force that is required? Okay. So we intend to find out force. So force is change of momentum per unit time. That would be change in speed, velocity per unit time. So mass is given 90. Change in velocity would be it emerges with 20 meters per second, right? So final speed is zero, but once it was not pumping, so it should be zero. Sorry, final speed is 20, initial speed should be zero because once the pump was not switched on, so water has zero speed. So time is given, which is 1 minute, that's 60 seconds. So once we solve this out, what do we get? We get 30 Newton. That's A. So then it says the mass is placed on a frictionless slope inclined at 30 degrees to the horizontal. So that's the idea here. So this is 30 degrees and this is the mass. It says the mass is then released. What is its acceleration? So there is no friction. So acceleration for anything that is placed on an inclined plane, we did that numerous times. That is g sine theta. So reason for this is if let's say we have this as the weight. So we can split this weight into two components. This would be the perpendicular component. That's actually W cos theta, since this is 30 degrees. And this would be the parallel component. That would be W sine theta. So this brings this object down. So if I relate W sine theta to the resultant force, so this becomes mg sine theta is equals to ma. M gets cancelled, so we can get this term A is equals to G sine theta. So basically A is unknown, G is 9.81 times sine 30, which makes us half. So this would be somewhere around 4.91. So we have A, 13 as A. Then in question 14, we say the ship of mass this much 8.4 exponent 7 is approaching a harbor with a speed of 16.4 meters per second. By using reverse thrust, it has to maintain a constant stopping force of this much. How long it's how long will it take to stop? Okay, so we have again the same formula that's relevant. That would be change in momentum per unit time. Force is given, that should be 9.2 exponent what 345. Mass is given, which is 8.4 exponent 7, and then it should be final speed and initial speed. So it has to stop. That means finally it has to stop. Initially it's 16.4 and time is unknown. So basically time shouldn't be negative, right? So we can just assume this is the case for deceleration. So we can proceed with that. So t is equals to 8.4 exponent 7 times negative 16.4 over 9.2 exponent 5. So we can just ignore this sign, negative, and we can figure this out. So the value I'm having is, uh, we have to also convert it into minutes. Okay. So it is 8.4 exponent 7 multiplied by 16.4, dividing it with 9.2 exponent 5 gives me around 1497.3 seconds. So if I see options, so in seconds, I don't have these options. Let's see minutes. So if I convert this time into minutes, so I'm having 24.9. Once I divide it with 60, I'm getting 24.9. That's 25 minutes, right? And that's nice. So I think all of these questions are similar, right? So we can just skip to some more difficult and new questions. So let's try question number 17 here. So question 17, you guys can go read this question first before I solve it. So once you are done reading, then I'm going to try this question. So I'll wait for a few minutes. Okay. So it says an elastic collision occurs, right? So these are going to collide elastically, and this is stationary. That means if I apply momentum conservation and I'm taking this as positive, so that would be mv plus 4m into 0, right? Is equals to. So now they're separating, right? So momentum conservation is still valid. So this is the equation here. So that's m multiplied by 3v over 5. So this would be a negative velocity because we are assuming this to be positive. And then this would be 4m times v. We don't know what that is. So let's find that. So let's not assume that v. Let's do that x because that's the unknown thing. So first figure out this x here. So this would be mv is equals to minus 3mv over 5 plus 4m x. So if we bring that there, so basically this would now be mv plus 3mv over 5 is equals to 4m. So this would be 5mv plus 3mv over 5 is equals to 4mx. So this is 8mv over 5 is equals to 4mx. So m gets cancelled. This 4 makes this 2. So this would be 2v over 5 is equals to x. So that's the x value here. Okay. They wanted us to find out the kinetic energy. So we have mass. So that's half mass v squared. So that's 2v over 5 4 squared. So that's going to be 4m times 4v squared over 25. So that's 16 over 50 mv squared. So this would be C. Okay. Question 18 says the graph shows the variations of weight and mass. Okay, what is the value of the acceleration? So acceleration would be W over M. So weight is 4 and mass is this is 0.5, that's 1, that's 1.5, that's 2.5. So that's 2.5. So 4 divided by 2.5, it is going to be 1.6 meters per second squared. So that's basically B. Okay. Then, well, these are action reaction questions. So let's try them anyways. So 19 is basically going to be a slow vehicle and a fast vehicle travel towards each other in a straight line and then collide. Okay, slow vehicle and fast vehicle. They are coming towards each other. Okay, and then they collide. What outcome is never possible? Okay, what is never possible? Both vehicles stop? Well, they can stop. Yeah, they can actually stop. So this seems possible. Only one vehicle stops. Yeah, basically, maybe the slower vehicle stops and faster vehicle, continues to move on. Depends on the mass, but that's possible. Fast vehicle, the speed increases. Well, this is not possible at all because if they're coming head on, so there is no possible way that speed has to increase. Speed has to decrease. So C is not possible. I'll go with C. 20. It says a man stands in a lift that is accelerating downwards. Okay. Which statement describes the forces exerted by the man on the floor. So forces exerted by the man on the floor. Okay. So if it goes basically down, that means the resultant force is down. So that means weight and tension are related here. So resultant force would be W minus T. Okay. So that means resultant force would be equals to resultant force plus T is equals to W. Okay. That means if we are working for the force exerted by the man on the floor. Okay. So the force exerted by the man on the floor should be something other than, well, actually, it would be weight, right? Because he is going to exert the force equals to weight. No, it is not going to exert the force equals to weight. So let's do one more thing. Weight, tension, and let's say that's normal reaction. And this is the force we are interested in, X. So that is going to be now decreasing weight. Yeah. So since it goes upwards, so is it equal to the weight of the man? That's what we have discussed. Weight is equals to tension, not the upward force. It is greater than the force exerted by the floor on the man. So if that's the case, this man should be coming down the floor of the elevator, right? Well, that's not happening. It is less than the force exerted by the floor on the man. So in that case, this guy has to be somewhere here in air. So that's not possible still. It is less than the weight. Yeah. Basically, since weight is now being reduced through this reaction force, so I'll go with D. 20 should be D. Well, these action reaction questions have taken a toll on us. So I think you guys can try this now. Well, most of the questions are related to what we already discussed in classes. Non-uniform motion is still basically projectile motion. So we have done those. Plenty of questions related to it. Uh, so if we want to try this one, which looks quite difficult, but it is actually very easy. And just going through some questions, let's see how it goes. So it says question 10, two blocks of masses M and M are joined. Well, we can see that. And this guy is going down and this guy is going up. So what is the acceleration? So if I figure out the resultant force on this mass, so weight here and that's tension here, right? So that would be W minus T is equals to MA. And for this guy, weight should be this way, tension should be this way. So that would be T minus W is equals to MA. Okay. If we have to work out the acceleration. Well, acceleration then can be equated by just adding them up. So what do we have? If I just add them up. Hmm. So this is going to be 0. That's going to be MA plus MA. Okay. So no, no, no. No, 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 no. Because that would be different. So I'll have this W minus W. Yeah. That won't be 0 because W is mg, right? So this W guy has to be mg and this W guy has to be mg. Okay, so this would be mg minus mg is equals to ma plus ma. So let's do m minus m over m plus m. This would be g and this would be a, right? So do we have any option similar to that? M minus m over m plus m. Yeah, we have. We actually have. Right? Good. Nice. Let's see. What do we have next? All simple questions, nothing difficult here. Well, this looks like a difficult question. Let's try this. So 4.3. Okay, it says, first you guys can read this question. So it says, which equation is not correct? Okay. So let's see what's happening in A. So A represents kinetic energy. So kinetic energy would be m1 u1 squared, right? Plus m2 u2 squared. equals to m1 v1 squared plus m2 v2 squared. How do I figure out this equation using kinetic energy? Because this represents an elastic collision, right? And I'm not writing 1 upon 2 because 1 upon 2 gets factorized and it gets cancelled, right? So that doesn't mean anything here. So if I just bring this guy there and bring this guy here, so this would be m1 u1 squared minus m1 v1 squared. Well, that would be this equation, right? So this looks absolutely fine. How about if we try this question, question B? So it says V2 plus U2. So speed of approach, let's say we take U1 plus U2. So this would be U1 minus U2 because if I'm assuming this to be positive, so approach has to have a negative sign, right? Then after collision, it should be like V2 minus V1. So speed of approach equals to speed of separation. So do we have something like this? U1 plus V1 is equals to V2 plus U2. So well, B is still fine, right? We can have that. We can just see that speed of approach equals speed of separation, right? So the important part is I have assumed this to be positive. So this positive and this has to be greater than this. That means V is fine. How about C? So C looks like momentum conservation. Like it's like M1 U1 plus M2 U2 equals to M1 V1 plus M2 V2. So if you bring this guy here, shift it here, this is what you're going to get. So A, B, and C are all fine. So this should be D. D is all the equation which is not fine. Okay, let's try another question here. So it says the diagram shows a particle P traveling at speed V about to collide with a stationary particle Q of same mass. Well, that's very simple. So if this goes on to hit something which has the same mass, both let's say are 10 grams. So this was stationary. So once they collide, what happens? So this guy has to move with V and this should become stationary, right? If it is an elastic collision. So do we have that statement rebound, rebound, travel? It has to be standstill, yeah. So I'll go with simply D. Because there is no loss or gain of energy, so it has to be D, right? Okay. Let's try another question. So what happens here? Okay, so it says first let's read this question. What are the speeds of the two gliders after the collision? They want us to find out the speed after the collision. Okay. So this is glider P, okay. So let's assume elastic collision. Well, they must have said this is an elastic collision. Yeah, it says so. Momentum conservation would be zero point 0.3 times 1.2 if I assume this to be positive, plus this is 0.6 times 1.8. I am taking this as positive equals to, I don't know the speed, but I do know the mass. So this would be 0.3 x and this should be, if I assume this to be positive, then this has to be negative. So 0.6 y, right? So this negative comes here because of the direction. So zero point 0.3 times 1.2 is 0.36. 0.6 times negative 1.8. So this comes out to be 1.08. Okay. So 1.08. I just need to see. Give me a minute. Zero point 0.6 times 1.8. So yeah, that's 1.08. And that's fine. Then, okay. So this would be 0.3x minus 0.65. Now, 0.3x minus 1.08 and 3x minus 1.08 is negative 0.72. Negative 0.72. So I have one equation and I can also convert it this way. So this would become 0.65 minus 0.3x, right? So that's my one of the equations when I applied momentum conservation. So it is momentum conservation before collision and after collision, right? Now I can apply approach and separation. So speed of approach basically is 1.2 plus 1.8, and speed of separation would be v1, sorry, not v1, let's do x minus y, right? So 1.2 plus 1.8 would be 3. So that's 3 is equals to x minus y. So now we have these two equations. We can just plug this in the calculator and find out x and y, right? So let's try to solve it. So 0.72, 0.6x minus 0.3x. So if I bring x here, so this would be 3 plus y, right? And I can plug it here. So 0.72 is equals to point. Well, I'm not going to solve this. Just skip this part and solve it using a calculator. And you'll end up with C as your answer. That is what I'm getting through my calculator. Okay, let's go ahead. Okay, question 4. Question 4 says two objects. What is the speed of y after collision? This is what they want us to find out. Okay, never mind. So this would be very easy to work upon if we just did the question you're supposed to do today. So it has to be like momentum conservation, and then we can proceed up with the mass. Basically, we don't actually need momentum conservation. It's an elastic collision. So speed of approach would be 20 minus 12 equals to speed of separation. That would be v minus 10. So approach is basically going to be 8. That's v minus 10. So 8 plus 10 is going to be 18. So do we have 18? Yeah, we have 18, right? So that's the answer here. Question number 5. So question number 5, it says, I think you must have read this question. So it says, what statement about P and Q must be correct? Okay, they have to be correct. So it says, during the interaction between P and Q, some of the total kinetic energy is lost. Well, if if that's the condition, relative speed of approach is equal to the relative speed of separation. So that's not possible at all. Why? Because this represents an elastic collision, right? For an elastic collision, there is this condition valid, right? So elastic collision has no loss of kinetic energy. So A is absolutely wrong. B, during the interaction, momentum is lost. No, momentum is still not lost during any kind of collision. Momentum stays conserved always. So let's try then. See, the momentum of Q after the interaction is equal to the momentum of Q before the interaction. Yeah, this looks fine. So momentum of Q after collision equals momentum of P before collision. Why? Because they have the same, flotation, they have the same masses. So they're going to just interchange their speed, right? So if it was maybe 10 Newton second and it was, let's say, 5 Newton second, so it has to just interchange. So C is fine too. So values of the kinetic energy of P plus kinetic energy of Q before and after the interaction are equal. So, oh, sorry. They want us to find out the correct statement. C is the incorrect one. So C is still the incorrect one. Yeah. D is correct. Now, if I say momentum of Q after the interaction is equal to the momentum of P before the interaction, why is this wrong? So it has to state that momentum of Q and P after the interaction is equal to the momentum of P and Q before the interaction. So total momentum still stays conserved. Kinetic energy gets interchanged, right? So I'm really sorry. C is basically incorrect because it says only Q and only P. So I missed that part, right? Now, let's try question 6. I think this is very easy. A helium atom of mass M collides with a mole. The atom arrives at wall with a speed v. So this guy comes here with v. So momentum is mv. Then rebounds. So this should be negative v. So it has to be 2mv. That's it. Simply what, right? So I think we have done a lot of questions, right? I kind of did. Let's do this a few more. Few more. Let's see how it goes. So question 7. This is well a very good question, a very simple question. It says a nucleus collides with a stationary nucleus. Okay, it's the nucleus one. Okay, no other particles are involved. Which diagram is not possible? Okay, so we have to see where momentum conservation is not possible. So this was momentum along x-axis, right? Before collision. So momentum along x-axis before collision and momentum along x-axis after collision. So initially there was some momentum. So finally there has to be some momentum. So A is correct. And Y gets cancelled out, right? Why? Because momentum here and momentum here should be equal and opposite. So at y, it has to be 0 because there was no momentum on y and no momentum on y should be present after collision. So A is absolutely correct. So this is possible. Let's find out B. So if we go on with B, so it's still y gets cancelled out because it's plus y and it's minus y. And then you can worry about the size, but we never know how fast this was going, right? Maybe this was going with a relatively slow speed on y-axis. This was going relatively faster. We don't know it, but still it has to cancel, and the only resultant momentum would be along x-axis. So that still is okay. So this is a correct statement, and this is possible. So these two are possible. Let's try C. So if we extend this, so we have x before and x after. Well, that's fine. But if we resolve these two, so this is not going to give us momentum cancellation. Why? Because they're both negative. So both negative never cancel out, right? They're both below y-axis. So C is not possible at all. Let's try D just to further confirm. Yeah, we still have positive and negative. This would be negative here, doesn't matter. So plus y and minus y here, that's still there, right? And x is there. So D is also possible, but C is not possible at all, right? So I'm too tired now. So if you have any questions other than this in dynamics, there were a few students who are coming up, sir, okay, please explain us dynamics. So I tried to do around 30, 40, 20, 30 questions. So do let me know. I'll do some more questions if there is a need, okay? No worries. Till then, take care. Allah Hafiz.